Hi, so let's continue our derivation of the Navier-Stokes equation from the equation of motion. And so that's the second part. In the previous part, this is the equation that we obtained, that I have reproduced right here. And I mentioned that I will be combining the transient term with the convective term. So that's going to be the object of this second video on the topic. All right, but perhaps before that, I'd like to just take care of the convective term here. So it's written as the nabla operator, the dot product. So you have that operator with rho uu. And well, because the density is essentially constant in space, for the moment, I am not going to consider it. What I want to do is write fully write that convective term using the xyz coordinates, well, for the sake of simplicity. All right. Okay, so this equals to, so the nabla operator is partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. So that's essentially a 1/3 matrix. Okay, so that's basically a vector, right? And that's going to be applied to our dyadic product, which will be written as, so the first component will be ux, then we're going to have ux, uy, and then we'll have ux, uz. On the second row, we'll have uy, ux, uy, and uy, uz. And finally, on the last row, we'll have uz, ux, uz, uy, and uz. Okay, so excuse me, this is a 3/3 matrix, right? So 1/3, take dot product of that vector with that 3/3 matrix, so that will give you again a 1/3 matrix or another vector. I should, the way I've written it, I should write it as also a line vector, but because I'm lacking of space, obviously, I will just write the result as a column vector. So what are going to be the different components of that column vector? Well, we apply the partial derivative term d over dx to ux, and you add it to d over dy ux, uy, and add d over dz ux, uz. So that's going to give us d over dx ux plus d over dy ux, uy plus d over dz ux, uz. Okay, so that's for the first component of our vector. Second component will be d over dx, so this time it's applied to the second row of the matrix. That's going to be uy ux plus d over dy uy and plus d over dz uy uz. And finally, we're going to have d over dz applied to uz ux plus d over dx plus d over dy applied to uz uy and plus d over dz applied to uz. Okay, and next, what I want to do is just look at the first component of our vector, just for you to realize something. So I'll copy pasted it here, right? Just highlight it, put it here. Okay. And I will further apply the partial derivative term. So that's going to be written as ux dux over dx plus dux over dx ux. And we have ux duy over dy plus duy over plus dux over dy times uy, and plus, so again, ux duz over dz plus dux over dz times uz. Okay, so 3 combinations of term. This is here. Let's use different colors, perhaps some orange here. This is here, and finally a little bit of pink for the final term. And I did that because I want you to realize something. This comes from velocity vector. The partial derivative with respect to x comes from the nabla operator, and again we have u here. Similarly, the second term, it starts with the nabla operator, which is applied to the velocity, and the whole thing is multiplied also by the velocity component. So the point of doing this is actually I wanted you to realize that delta the nabla operator, so the divergence of the dyadic product actually equals to the dot product of the velocity vector with that nabla operator multiplied by u plus the dot product of that nabla operator in u, so basically divergence of u, and again multiplied by u. And we're going to use that identity in our momentum equation. So now we're getting back to these two terms, the transient term and the convective term, and we're going to combine them. So we had initially the partial derivative of rho u with respect to the time, and plus, if we combine them, that's going to be plus the dot product of that nabla operator and rho uu. Okay, so now let's differentiate the terms. So the first one, the transient term, will give us rho du over dt plus u d rho over dt. Okay, let's highlight here. And now what about our convective term? Well, according to what we've just written, there's going to be plus rho times, so here we have u dot and that inverted delta times u, and plus rho u, oops, sorry, no, it's correct, plus divergence of the velocity times u. Okay, and okay, let's highlight them with similar color. Fine, so what I want to do next is reorganize the term a little bit. So I will take the first term, rho du over dt, and I'm going to combine that with the dot product of u and that operator times u. Okay, so essentially I'll use different colors here. Try to be not too, I'm taking this term and I'm combining it with this term, and I put them here. Okay, and I think you see where I'm going. You can see what I want to do next. I will take the two remaining terms and I will have u times 0 over dt plus rho delta, sorry, not inverted delta, times divergence of the velocity. Okay, and that's for these two terms here. And now perhaps you recognize the equation of continuity. And so, you know, this is going to be 0. In other words, the only surviving term is a different color now. What's going on? Well, du over dt plus u dot nabla u, and that's what we call substantial derivative of the velocity.